All right, as promised, I'll get you guys the first section for anybody that was absent yesterday um, or wants to reread it. All right, so section one, models of the atom, what you'll learn. Discovery of subatomic particles, how the atom model was developed, what a nuclear atom is made of, that all matter is made up of atoms. Before you read, what is the smallest thing you've ever seen? Was this made up of smaller parts? A lot of things that are small are still made up of smaller things. You looked at anything under a microscope, maybe. That might be the smallest thing, like a cell. Are cells made of smaller things? Sure. First thoughts. By the way, it says outline. If you guys want to outline this, by all means, go for it. First thoughts. Do you like mysteries? Are you curious? People are usually curious. They always want to know something that is not easy to understand, or they want to know about something they can't see. For example, people first began wondering about what matter was made of more than 2,500 years ago. Some early thinkers thought that matter was made of tiny particles. They thought you could cut matter in half, and then in half again many times. Finally, you would have a piece so small that you could not cut it anymore. They named this smallest piece the atom. The word atom means cannot be divided. How do you describe something that you can't see? Thousands of years ago, people could not prove that atoms existed. In early times, scientists did not do much in the way of experiments. They discussed their ideas until they agreed on them. Even if they wanted to experiment to find out about atoms, they could not have because they didn't know much about what we call chemistry or the study of matter. Equipment that scientists use today to study matter had not yet been invented. Atoms were still a mystery as recently as 500 years ago. On the side here in the margins, we got our first question. Explain why didn't early scientists do experiments? Well, they liked to debate things as a way of thinking about them and learning about them, and they didn't have as good of equipment or just scientific background knowledge in general. A model of the atom. For a long time, no one had new ideas about the atom. Finally, in the 1700s, scientists started thinking about atoms again. Chemists were learning about matter and how it changes. They put substances together to form new substances. This section really has a lot of the word substances. It's quite a lot. They also took substances apart to find out what they were made of. Scientists found that some substances could not be broken down into simpler substances. I got a student that's chuckling. They called these substances elements. An element is matter made up of only one type of atom. For example, iron is an element made up of only iron atoms. Silver is an element made up of only silver atoms. What was John Dalton's concept of the atom? John Dalton was an English school teacher in the early 1800s. He had these ideas about matter. 1. Matter is made up of atoms. 2. Atoms cannot be divided into smaller pieces. 3. All atoms of an element are exactly alike. And 4. Different elements are made of different kinds of atoms. Dalton thought of an atom as a hard sphere or ball, like a tiny marble. How was Dalton's theory tested? In 1870, an English scientist named William Crookes experimented with a glass tube as shown in the figure below. Let me scoot down a little bit here. The tube had almost all the air removed from it. The tube had 2 pieces of metal called electrodes inside. The electrodes were connected to a battery by wires. So here we have our figure, the electrode on each side. Okay, negative side is called a cathode, positive side is called an anode, and then he has an object here shaped like a German cross, iron cross, and then the cathode rays are emitted across the tube. It tells us here, number 2, go ahead and draw a circle around the positive side. Okay, positive, so we'd say this is the positive side, and this is square around the negative side. So that's what we would do if we actually had a workbook. What is a cathode ray tube? An electrode is a piece of metal that conducts electricity. An anode is an electrode with a positive charge. The anode is connected to the positive side of the battery, as shown here. The cathode is an electrode with a negative charge. The cathode is connected to the negative side of the battery. In Crookes' tube, the cathode was a small metal disc. The anode was a larger metal disc. In the middle of the tube was an object shaped like a cross, as you can see again in the figure. What happened in Crookes' tube? When Crookes connected the battery, the tube lit up with a green glow. The shadow, or a shadow, of the cross appeared on the anode. Crookes believed that something was flowing from the cathode to the anode. The cross was blocking the flow, causing a shadow. Crookes thought that the glow was caused by rays, or streams of particles. He called the rays cathode rays because they came from the cathode. Crookes' tube is called a cathode ray tube, or CRT. Many televisions and computer monitors, maybe not anymore, but when this was written, have a type of CRT, like 90s, right? Discovering charged particles. Some scientists were not sure that cathode rays were streams of particles. They thought the rays were just a form of light. In 1897, an English scientist named J.J. Thomson did an experiment with cathode rays. He placed a magnet beside a cathode ray tube. The magnet caused the cathode rays to bend. Light can't be bent by a magnet, so the beam could not be light. Thomson concluded that the rays were made of charged particles of matter that came from the cathode. He had discovered electrons. Question on the side, why could the cathode rays not be light? Because light can't be bent by a magnet. What are electrons? Thomson did many more experiments with CRTs. He made cathodes of different types of metals. He also used different gases in the tube. Each time the same particles were produced, electrons. Thomson decided that cathode rays were negatively charged particles of matter, which electrons are. He knew that opposite charges attract each other. He decided the particles in the CRT were negatively charged because they were attracted by the positively charged anode. These particles are now called electrons. Electrons are negatively charged particles. Thomson thought that electrons are a part of every kind of atom because every kind of cathode material produced electrons in his experiment. Thomson's results showed that particles smaller than atoms do exist. We call an electron a subatomic particle. Do you remember the other two? Protons and neutrons. What did Thomson's discovery actually mean? So, big deal. Why does it matter? Thomson's discovery meant that atoms must have negatively charged particles called electrons inside of them. If that is so, why isn't all matter negatively charged? Thomson believed that atoms also must have some positive charge. That way the negative and positive charges would neutralize each other or cancel out. Describe, number 4 on the side, why did Thomson think all atoms contained electrons? Because he tried a bunch of different materials, and no matter what he tried, they kept releasing those negatively charged particles. So if everything he tries keeps on doing it, stands to reason that all atoms have them. How did Thomson model the atom? Thomson made a new model of the atom based on his findings. Dalton thought of an atom as a solid ball that was the same throughout. Thomson pictured a sphere of positive charge. Negatively charged electrons were placed evenly in the sphere. In Thomson's model, an atom is something like a ball of chocolate chip cookie dough. The sphere of dough represents the positive charge. The chocolate chips represent electrons, which have a negative charge. And my daughter just handed me this picture of, she calls it the plum pudding model. Yes, absolutely. Very similar. This is Thomson's atomic model. So in our workbook, it's talking about chocolate chip cookie dough, but he called it the plum pudding model or in parentheses, she also has written chocolate chip cookie model. There, oh gosh, there it is. If it will focus. No, not so much. Anyway, thank you for that, daughter number one. Where was I? Did I get all the way to the bottom here? The sphere, the sphere of dough represents the positive charge. The chocolate chips represent electrons, which have a negative charge. Cool. Compare and contrast. How was Dalton's model of the atom different from Thomson's? So instead of just being a evenly mixed up sphere of like one thing, Thomson has like the overall substrate being positive, and then you have these negatively charged particles kind of stuck up in it, kind of mixed in. Still wrong, but getting there. We're getting there, right? Every model keeps getting better. Rutherford's experiments. In 1906, Ernest Rutherford did an experiment to find out if Thomson's model of the atom was correct. He and his coworkers fired alpha particles at a very thin piece of gold foil. Alpha particles are positively charged bits of matter. Two positive particles repel or push each other away, so alpha particles would be repelled by matter that is positively charged. Also, in the next section that we've already read, we learn more about alpha particles. Look at the figure below. Alpha particles were fired at a sheet of gold foil. The foil was only 400 nanometers thick. There was a fluorescent screen around the foil. The screen gave a flash of light each time it was hit by a charged particle. So here we have our device that is emitting alpha particles. They're going to pass through, he thought, most of them would pass through the gold foil and hit the other side. And when it strikes the other side, it would give a flash of light, this detector screen. So he did think that some of it would scatter, but most of it, vast majority, would go right through. Okay, that was what he was thinking. What he thought would happen, he predicted that most of the particles would pass straight through the gold and hit the screen on the other side. He didn't think that the gold foil contained enough matter to stop the speeding alpha particles. He thought that the positive charge in the gold atoms might cause a few minor changes in the path of the alpha particles, but not very often. That's what he thought. Does the figure show all particles passing through the gold foil? No, it shows some of them kind of bouncing around, doesn't it? A few particles bounce toward the source, too. So not just redirected a little, but bounced back, reflected back. Was Thomson's model wrong? Well, Rutherford's hypothesis made sense. Remember that in Thomson's model, the positive charge is neutralized by nearby electrons. Rutherford was so sure what his results would be that he had one of his students complete the experiment. He thought Thomson was right. Rutherford was surprised to find, however, that some of the alpha particles bounced backward, not just slightly deflected, but completely backward off the foil. How could he explain this event? He decided that the positively charged alpha particles were moving so quickly that it would take a large positive charge to make them bounce back. This meant that Thomson's model of the atom with an equal mix of positive and negative charge must have been incorrect. A model with a nucleus. Rutherford and his team had to explain these unexpected results. If Thomson's model was correct, an alpha particle might be affected slightly by a positive charge in the atom and turn a bit off course. The large changes in direction that Rutherford observed would not be expected with this model. How were protons identified? Let's see. Are we ready to get this one? Nope, not ready for this one yet. Rutherford proposed a new model of the atom, shown in the figure. He hypothesized that almost all of the mass and the positive charge of an atom are crammed into a tiny space at the center of the atom called the nucleus. In 1920, his prediction was proved true when scientists identified protons. A proton is a positively charged particle that is in the nucleus of every atom. The almost massless electrons move in the empty space around the nucleus. What did Rutherford's model explain? His model explained that what happened in his experiment. Most alpha particles move through the foil with little or no interference because atoms are made up of mostly empty space. But if an alpha particle hit the nucleus of a gold atom, the strong positive charge in the nucleus repelled the alpha particle. The alpha particle then bounced backwards. Number 8, what are the particles floating? I don't like the word floating here, but around the nucleus of the atom. What do you think? What are these floating around
Electrons.
the nucleus? Yeah, they're electrons. Good. And again, I don't like the word floating, but whatever. They're moving around erratically.
Orbiting.
Yeah, no, I wouldn't use the word orbit. And we're going to read that here in just a second. Number 9, explain why did some of the alpha particles bounce off the gold foil? Because they were running in, they're positively charged, and they were running into other positively charged things. So they repel. All right. What did Rutherford's model not explain? Rutherford's model explained why some alpha particles bounced back. However, his model did not answer all the questions about the atom. For instance, an atom's electrons have almost no mass. In Rutherford's model, the only other particle in the atom was the proton. So the mass of an atom should be about equal to the mass of its protons. But the mass of most atoms is at least twice as great as the mass of its protons. So Rutherford's model didn't explain that. Where does the extra mass come from then? To explain the extra mass in an atom, scientists thought, well, there must be another particle in the nucleus. Is a neutron, this particle was called the neutron. A neutron is a particle that has the same mass as a proton, but has no electrical charge or is neutral. It was hard to prove that neutrons exist because the neutron had no charge, so they are not attracted by magnets, and they do not make fluorescent screens light up. It took 20 more years before modern experiments were able to show that atoms contain neutrons. When neutrons were discovered, the model of the atom must change again, right? The nuclear atom, shown in the figure, has a tiny nucleus, tightly packed with positively charged protons and neutral neutrons. Negatively charged electrons are found in the empty space around the nucleus. The number of electrons in a neutral atom contains the same number as the number of protons. So here we have the electrons flinging around. You could use the word orbiting, but that's not really correct, around this nucleus. And of course, this is not to scale, which is what we're about to read next. How big are atoms? Drawings of the nuclear atom, like this one, like the one above, can't show you the actual size of an atom. Drawings also don't show how small the nucleus is compared to the rest of the atom. It's kind of like the solar system model we did in class last week, where it's like, well, if we actually want to be to scale, we need a very large space. Anyway, imagine that the nucleus of an atom is the size of a table tennis ball, so a ping pong ball. The atom would have a diameter greater than 2.4 kilometers. So if the nucleus is, yay big-ish, was that over 1.5 miles, I think? I mean, that's quite a diameter for the whole electron cloud. Now you understand why most of the alpha particles in Rutherford's experiment went straight through the gold foil, because most of the atom is empty space. Yes?
What is an electron? What electrons are?
Oh, we're going to get to that next. Yeah, absolutely. Here we go. Identify how many protons are in this atom. How many electrons are there? So if we look really close, you can see the little plus signs on some of these. We got 1, 2, 3, 4, 5, at least 1, 2, 3, 4, 5, 6. So if we've got 6 protons and we have 1, 2, 3, 4, 5, 6 electrons, we have a neutral atom of carbon is what we have. And then number 11, explain what makes up the most of the atom. What?
I think it's the nucleus. Neutron.
Most of the atom is made of empty space. Haha, tricked you. Tricked you. Yep. All right, cool. Moving on. Further developments. Scientists first thought electrons orbit or travel around the nucleus of an atom, kind of like the planets travel around the sun. They thought that the negatively charged electrons were attracted to the positive charges of the nucleus, like the moon is attracted to the Earth by gravity. But scientists later learned that electrons are in constant, unpredictable motion. They're just flinging around. The motion of electrons cannot be easily described by an orbit. It is impossible to know or predict where an electron is or will be at any particular moment. These findings led to even more experiments about atoms. Can the behavior of electrons be explained? Scientists continue to struggle with how to explain the unpredictable nature of electrons. New theories and models were needed. One way to explain the movement of electrons is to think of them as waves instead of particles. Thinking of the electrons in this way helped scientists come up with the current model of the atom. What is the electron cloud model? So you're going to have your question answered. The latest model of the atom is the electron cloud model shown below. So here we have an electron cloud model. The electron cloud is the area around the nucleus of an atom where the electrons travel, where they're flinging around outside the nucleus.
I call them electron shells.
Shells? Well, there's when you're doing a Bohr model, you'd have like energy levels or shells, but in reality, it's just a cloud, like a haze around the nucleus where the electrons are buzzing around. Where was I? The electrons are more likely to be close to the nucleus than far away. That is because the negative electrons are attracted to the positive charge of protons in the nucleus. Notice that the cloud in the model has a fuzzy outline. There is no clear boundary because electrons could be anywhere within the cloud. And this may be the latest model of the atom, but it could certainly change. Scientists may find out new things about the atom. They may even decide that this model is just wrong. Science is always changing as long as scientists ask questions and do more experiments. On the side, draw and label. Shade the area of the electron cloud where the electrons are most likely to be, so they're going to be in here tight. And that's why it's shaded a little bit more darkly. More darkly. Darker? More darker. No, that's bad too. Nearer to the nucleus. All right. After you read, all right, here we go. We're at the end. Make sure that you study the mini glossary. If you want to put some of those in your notes, by all means. This one is about gold, what you know about gold. Don't overthink it. Like, what do you know about gold? You might look at the periodic table if you want to, but write a sentence or two. What do you know about gold? And then number 2 is an electron cloud model, kind of, sort of. Look at the 3 below. Label the parts of the current model of an atom. Explain what each part is. Just go ahead. Number 3 is optional. If you decide to outline the section, you'd be able to do number 3. Have a good day. If you're watching this during Thanksgiving break, you're amazing. You do have a couple of days before sections 1 and 2, end of section questions are due, but that is with the grace period built in. Okay, don't be late. I will not be taking late work weeks and weeks after they were due anymore. Okay, we should be in good practice by now. It's the middle of the second quarter. Have a good one.